Aviation history is full of experiments, but a select group of aircraft stand out for how strange they looked, how they flew, or the missions they were meant to perform. This list brings together 15 verified designs that push boundaries in pursuit of new answers to old problems. Some came from world wars, others from Cold War rivalries, and a few from commercial needs that seemed impossible to meet with conventional planes. From pancake-inspired designs to inflating cockpits, here are 15 of the strangest aircraft ever built by man. Number 1. Vought 5-173 Flying Pancake. The Vought 5-173 was the brainchild of Charles Zimmerman, an aeronautical engineer who believed that a nearly circular lifting surface could deliver remarkable short takeoff and landing performance. Backed by U.S. Navy interest during the early 1940s, the design served as a precursor to the more advanced XF-5U fighter. The Flying Pancake nickname came from its flat, disc-like shape, which looked nothing like a conventional airplane. The aircraft's planform was essentially a blended wing body with two massive propellers mounted on the leading edge. These props were designed to blow air across the wing, delaying stall and giving the aircraft excellent control at extremely low speeds. Unlike a typical fighter with long runways in mind, the V-173 was intended for operations from short naval decks or improvised strips. Constructed of wood and fabric to save weight, the demonstrator used two small Continental engines, far less powerful than the equipment envisioned for a production model. Despite modest thrust, its handling impressed pilots. Reports highlighted its ability to maintain control at walking speeds, and its stall behavior was unusually forgiving. The Navy originally planned to carry lessons from the V-173 into the heavier, metal-built XF-5U. But the jet age was arriving fast, and resources shifted away from prop-driven fighters. The program ended before full development, yet the V-173 left a technical legacy. Its data on prop wash over lifting bodies influenced later research into high-lift systems, reminding engineers that radical shapes could, at least in testing, deliver surprisingly stable flight. Number 2. Caproni CA-60 Transaereo. Around a century ago, Italian aviation pioneer Gianni Caproni proposed an aircraft that could cross the Atlantic with dozens of passengers on board. His solution was the CA-60 Transaereo, a flying boat unlike anything seen before. The machine sat on a large float hull and carried a massive triplane wing stack. The three sets of wings mounted one above the other, repeated 3 times down the fuselage. The configuration gave the CA-69 wings in total, paired with 8 engines spread across the structure. The designers imagined it carrying up to 100 passengers at a cruising speed that, on paper, would make transatlantic service possible. Its weight and drag were enormous, but Caproni believed sheer lifting area could overcome those limits. Initial testing began in 1921 with taxi runs across Lake Maggiore. On its first brief flight, the aircraft managed to climb to about 60 feet before instability set in. Structural vibrations combined with poor control responses, and the giant machine crashed into the lake, breaking apart on impact. Although repairs were discussed, the sheer complexity of the design and the scale of the damage ended the effort before a rebuilt version could be attempted. The CA-60 became a cautionary tale about pushing size and wing stacking without solving control and aeroelastic problems. Engineers studying the wreck noted drag penalties, unpredictable airflow across multiple wing planes, and control coupling that no pilot could safely manage. Number 3. Blohm Voss BV-141. During World War II, German engineers sought a reconnaissance aircraft with unmatched visibility for the crew. The company Blohm Voss proposed a radical solution, an asymmetrical layout where the engine and fuselage sat on one side and a glass-heavy crew pod extended out from the other. The idea was that the crew, sitting in the offset pod, would have a clear view in nearly all directions without obstruction. The BV-141 carried its single engine in a conventional nacelle aligned with the tail boom, while the glazed crew pod projected outward to the starboard side. Inside, space was provided for cameras, a pilot, and observers, with defensive armament arranged to cover the vulnerable approaches. It looked unbalanced at first glance, but wind tunnel tests and flight evaluations confirmed that the aircraft was stable and controllable despite its unconventional form. Pilots who flew the BV-141 reported it handled well, with no unusual tendencies in roll or yaw. Performance was respectable for its intended mission profile, though it never matched the top-end speeds of fighters or bombers of the same period. The aircraft's biggest limitation was not aerodynamic but logistical. Wartime Germany faced shortages of suitable high-performance engines, and those available were prioritized for proven designs such as the Focke-Wulf FUF 190. Only a small number of BV-141s were built before the program was halted, but the experiment left a clear message. Asymmetry could be made to work in flight if carefully balanced. While it never reached mass production, the aircraft influenced later thinking and surveillance design, proving that efficiency and visibility sometimes required stepping far outside conventional symmetry. Number 4. Bartini-Beriev, VVA-14. In the late 1960s, the Soviet Union tasked engineer Robert Bartini with designing a patrol aircraft capable of tracking NATO submarines. The specification demanded unusual versatility. It had to operate from both land and water while using ground effect flight near the surface to extend range and endurance. The result was the VVA-14, a striking amphibious jet with a boat-like hull, twin main engines mounted high above the fuselage, and provisions for additional lift jets. The design aimed for vertical or very short takeoff ability, though the prototypes that actually flew never received the full complement of lift engines. Test flights showed the aircraft could transition between water and land, and it handled reasonably well at a range of altitudes. Its distinctive configuration gave promising performance when skimming close to the surface in ground effect, which was expected to provide efficient long-duration patrol profiles. But serious issues soon appeared. Integration of the unused lift modules proved more complicated than anticipated, and systems reliability fell short of operational standards. Limited resources and shifting program priorities within the Soviet military also slowed progress. Only a few prototypes were built, and none reached the intended full capability. Yet the VVA-14 still contributed useful data on amphibious jet operations and ground effect aerodynamics. Number 5. Aerospaceline's Pregnant Guppy and Super Guppy. While the space race with the Soviets was at its height, NASA faced a logistical problem, moving oversized rocket components across the United States. Traditional rail and sea transport was too slow for the tight schedules of the Apollo program. Aerospaceline's answered with the Pregnant Guppy, a heavily modified Boeing 377 Stratocruiser fitted with an enormous bulbous fuselage. The design provided a cavernous cargo bay accessible through hinged fuselage sections and reinforced structures. The Guppy's strange appearance was matched by its utility. It could carry rocket stages, satellites, and other equipment in a single trip, cutting weeks off delivery time. Its successor, the Super Guppy, expanded capacity further and remained in use for decades, hauling everything from NASA modules to aerospace industry hardware. Operationally, the aircraft carved out a niche. They were slower than jet transports and required careful handling during loading, but their ability to move outsized cargo by air saved both time and cost compared to alternatives. The service proved so valuable that even after Apollo, the Super Guppy continued flying specialized missions, including supporting the International Space Station program. Number 6. Goodyear Inflatoplane, an aircraft that could be packed into a box, inflated like a raft, and flown out of enemy territory. Sounds like science fiction. Yet that was the promise of the Goodyear Inflatoplane. Built from rubberized fabric, the airframe stiffened once inflated, forming wings, a tail, and a nose-mounted piston engine. The military envisioned it as a compact rescue tool, small enough to drop by parachute and light enough for a single pilot to operate. Crews could inflate it in minutes, attach the engine, and use even short, rough strips for takeoff. Flight testing proved it was controllable and capable of performing basic missions. The weaknesses quickly became obvious. A single puncture could compromise the structure, and the aircraft offered little protection against weather or enemy fire. Harsh conditions, turbulence, or hard landings placed stresses that the fabric body was never meant to withstand. Field maintenance was equally impractical, since patches required controlled conditions. Despite showing that inflatable structures could be adapted to aviation, the inflatoplane was too fragile for combat or rescue use. The program was shelved, but its experiments paved the way for later inflatable technologies in space habitats and emergency shelters. Number 7. Delackner HZ-1 Aerocycle. The Aerocycle was pitched as a flying jeep, a compact platform meant to give a single soldier the ability to hover and scout above the battlefield. Instead of a cockpit or fuselage, the pilot stood on a small frame directly above two counter-rotating rotors. Control relied almost entirely on body movement. Shifting weight forward, back, or sideways tilted the rotors to change direction. While it sounded intuitive, the workload was constant, demanding non-stop corrections just to stay balanced in the air. Flight tests exposed the risks. Turbulence or a sudden gust could overwhelm the operator, and the exposed blades left no margin for error. Stability problems, combined with the physical strain of standing throughout a mission, made it clear that the machine was unsafe for field use. Accidents during trials confirmed its shortcomings, and the aerocycle was abandoned before mass production. Even so, it demonstrated the limits of personal rotorcraft without enclosed protection, guiding later efforts towards safer vertical takeoff and landing approaches such as ducted fans and tiltrotors. Number 8. Lockheed XFV Salmon. Speaking of vertical takeoff vehicles, here we have one of the strangest attempts of the Cold War, the Lockheed XF-5 Salmon. Conceived as a tail-sitter interceptor, it was designed to rise vertically from its tail and then transition into horizontal flight, giving the Navy a way to operate high-performance fighters from small ships or improvised bases. The design used a cruciform tail that doubled as landing gear and an Allison turboprop, driving huge contra-rotating propellers. In theory, this provided the thrust and control authority to manage vertical flight, but in practice, the engine fell short of the power needed for safe transitions. Testing therefore relied on temporary landing gear, with the aircraft flown conventionally while engineers studied its handling and tried limited transition maneuvers. Pilots found the workload extreme, especially during landing attempts where even small errors could prove disastrous. The thrust deficit meant true vertical takeoff or landing was never demonstrated. By the late 1950s, tailsitters like the Salmon and its Convair counterpart were overshadowed by more promising approaches such as tiltrotors, tiltwings, and liftjet concepts. The program was canceled, but it left behind useful data on vertical transition, aerodynamics, pilot workload, and structural stresses. Number 9. Convair F-2Y Sea Dart. The Convair Sea Dart was born from a U.S. Navy requirement to field a supersonic jet fighter that did not rely on carriers or long runways. The answer was unconventional, a seaplane fighter capable of operating directly from open water, giving the Navy more deployment flexibility. Its design centered on retractable water skis that allowed the jet to skim across the surface during takeoff and landing. Engineers added spray suppression features around the intakes to prevent water ingestion at high speeds. But these systems introduced new complexities. On paper, the Sea Dart promised Mach-class performance combined with ocean basing. Testing revealed a very different picture. The aircraft managed takeoff runs and demonstrated ski retraction in flight, but stability during acceleration was poor. High vibration, spray interference, and control issues made the jet difficult to handle. Tragedy struck during a demonstration when one prototype disintegrated mid-air, killing its pilot, which cast further doubt on the program. Beyond technical hurdles, the operational logic weakened. Maintaining jet fighters in saltwater environments proved daunting, and performance never matched land-based aircraft. Sea state restrictions meant the aircraft could only operate in relatively calm waters, limiting its tactical use. The program was eventually canceled, but it left behind valuable data on hydrodynamic skis, intake protection, and seaplane jet operations. The Sea Dart stands as the only supersonic seaplane ever to fly, a bold but impractical detour in naval aviation. Number 10. Kalinin K-7. The Kalinin K-7 was one of the most ambitious aviation experiments of the 1930s, conceived in the Soviet Union as a multi-role giant. Its thick, broad wing was designed not only to provide lift, but also to house crew stations, equipment, and passenger compartments. Twin-tail booms and multiple vertical fins extended the structure, giving it a distinctive profile unlike anything else flying at the time. To power such a massive frame, engineers mounted 6 engines across the leading edge of the wing, with an additional pusher unit fitted at the rear. But metallurgy and production methods of the period imposed severe limits. The steel tube structure, while strong, proved heavy and vulnerable to aeroelastic vibration, a phenomenon poorly understood at the time. Test flights showed both promise and peril. The aircraft successfully lifted into the air, validating its lift distribution and payload potential. Yet vibration soon emerged as a critical flaw, shaking the airframe at certain speeds. On its 9th flight, structural failure caused the K-77 to crash, killing 15 people and forcing a hard reassessment of the design. The K-7 had been envisioned as a long-range bomber, transport, and even civil airliner, with proposals to carry 120 passengers. Redesigns were attempted, including plans for lighter construction and altered tail layouts. But the accident and shifting resources meant the project was abandoned. The fatal crash ended any hope of operational service, but the program still left useful data. Engineers studying the wreck learned more about how vibration affects large-span wings and where structural reinforcements were most needed. Though the K-7 never advanced beyond prototypes, the effort helped refine Soviet thinking on heavy transports and underscored how far material science still had to go. Number 11. NASA Done. Oblique wing. NASA's Adun was built to test one of the boldest aerodynamic ideas of its era, a pivoting wing that could rotate up to 60 degrees. The hope was to cut drag at higher speeds without the heavy mechanisms that came with full swing-wing aircraft. The jet carried a slim fuselage with a central pivot mount that allowed the wing to skew. As the angle increased, engineers had to account for unusual load paths and the way control laws shifted in flight. Pilots reported that at modest sweep angles, the aircraft remained controllable, but the further the wing rotated, the more complex yaw and roll interactions became. Testing stayed in the subsonic regime, yet it provided valuable insight into aeroelastic coupling and stability trade-offs. The Adun proved the oblique wing could fly, but it also showed the configuration brought penalties that outweighed the gains. No operational aircraft adopted the layout, though the program left behind hard data for later asymmetric wing research. Number 12. Mil V-12, Homer. The Soviet Union set out to build the largest helicopter in history with the Mil V-12, known by its NATO codename Homer. The concept was straightforward: create a heavy-lift machine that could carry enormous payloads over short ranges, filling roles that neither airplanes nor smaller helicopters could manage. Its design featured two massive rotors mounted side by side on wing-like outriggers, each driven by twin engines. The aircraft spanned nearly as wide as a Boeing 747 and could lift over 40 tons, setting world records for payload capacity that still stand today. Test flights demonstrated the V-12's raw lifting power, but they also exposed the enormous engineering burden that came with the design. Managing vibration across its transmission system, synchronizing gearboxes, and handling crew workload pushed available technology to the edge. Pilots found it flyable, but every sortie demanded precision and heavy maintenance support. Only 2 prototypes were completed. By the time they flew, strategic needs had shifted, and more practical heavy-lift helicopters like the later Mi-26 offered similar capabilities with less complexity. The V-12 never entered production, but it remains unmatched in payload achievements and provided data that influenced subsequent rotorcraft engineering. Number 13. Douglas X-3 Stiletto. Few aircraft looked as radical as the Douglas X-3, nicknamed the Stiletto for its long, needle-shaped fuselage. The project was intended to push U.S. research into the sustained high-speed realm, using tiny wings and a slender body to minimize drag. Engineers hoped it would explore flight behavior near Mach 2, giving valuable insight into stability, control, and structural heating. On paper, the aircraft should have been a leap into the supersonic future. In reality, its engines fell short. The turbojets installed could not deliver enough thrust to reach the speeds originally envisioned. This forced the X-3 to operate at lower performance levels, requiring extremely long takeoff runs and leaving little margin for experimental flexibility. Despite the shortfall, the X-3 still produced important data. Test pilots recorded how the airframe responded to high-speed conditions, especially the aerodynamic flutter and heating effects that became crucial considerations in later supersonic aircraft. It also highlighted the challenges of extremely small wings, showing the trade-offs between drag reduction and controllability. Ultimately, only one X-3 flew, and the program was retired without hitting its ambitious performance targets. Yet its findings fed directly into the design knowledge that shaped fighters like the F-104 Starfighter and influenced materials and structural approaches in later programs. Number 14. McDonnell 10F-85 Goblin. Among the strangest U.S. jet prototypes was the McDonnell XF-85 Goblin, a tiny parasite fighter designed to ride inside a bomber's bomb bay. The idea was simple in concept: launch the Goblin mid-mission to defend the bomber formation, then recover it back onto a retractable trapeze system. Its compact size was meant to make the entire operation practical without redesigning the bombers themselves. Testing quickly showed how difficult the idea was to execute. Pilots struggled with turbulence when trying to latch onto the trapeze, and recovery attempts often ended with the Goblin bouncing off or missing the docking point altogether. The workload in such conditions was exhausting, and each sortie underlined the impracticality of routine use. Beyond the docking challenges, the Goblin's performance was underwhelming. Its range and speed were inferior to contemporary land-based interceptors, meaning it could not realistically hold its own against frontline enemy fighters. By the time the prototype was flying, strategic thinking had already shifted toward aerial refueling and long-range escorts, which solved the same problem without such complexity. The XF-85 never advanced beyond prototypes, but the docking data it produced informed later research on aerial capture and recovery. The Goblin itself remains one of the most unusual attempts at protecting bombers during an era of rapid innovation and shifting doctrine. Number 15. Sikorsky S-72 X-Wing. The Sikorsky S-72 was designed to test one of the boldest rotorcraft ideas of the Cold War, a stop-rotor system that would let a helicopter transform into a fixed-wing aircraft mid-flight. The concept, nicknamed the X-Wing, proposed using 4 blades for vertical lift, then locking them in place to act as wings for high-speed cruise. Technically, this demanded a system capable of halting and re-accelerating the blades under extreme loads. Engineers had to solve how to transfer lift from rotating to fixed mode without losing control or overstressing the airframe. Precision in timing and load management was critical, as even small misalignments could cause catastrophic failure. The test campaign moved cautiously. The S-72 airframe flew conventionally, with extensive ground runs exploring the mechanics of stopping and restarting blades. But the full stop-rotor transition was never achieved in flight. The complexity of controls, propulsion synchronization, and structural stress proved harder to tame than the technology of the day could manage. Although the program closed without reaching its ultimate goal, the X-Wing shaped later thinking about hybrid vertical lift concepts. Data from the S-72 fed into broader research on high-speed VTOL, where engineers continue to weigh the trade-offs of rotor-borne hover against wing-borne cruise. Aviation has produced countless strange ideas, but the 15 aircraft here stand out for pushing the limits of design and imagination. Some aimed at solving military problems, others chased commercial dreams, and many simply tested whether physics would cooperate. Few succeeded in service, yet every one of them left behind insights that influence future programs. From inflatables and parasite fighters to giants like the Kalinin K-7, these projects show how innovation often comes through trial and failure. If you enjoyed this look at aviation's strangest machines, subscribe for more deep dives into unusual aircraft history, and tell us which one you'd dare to fly.